Hey, good morning, guys. Assalamu alaikum. Welcome back to grade 12, Physics by Inspired Teams, where in today's lesson, we are going to be continuing with rate of reactions for chemistry. Okay, so before we continue, what we'll do today is we'll finish up this Maxwell-Boltzmann graph. We'll go through some other concepts that I'd like to go through, and then we'll go ahead and do a question. Okay. Let me get that memo 1 second. We'll start shortly. Okay, cool. So just to revise, right, what we've done so far, we've talked about rate of reactions, of course, and what does rate mean? Okay, so remember when we divide something by delta T, we said that that describes something as a rate, okay? And we discussed it here in terms of displacement, the rate of change of displacement that gives us velocity, right? But dividing by that delta T gives us that rate of change. Okay, so here we're discussing what is the rate of a reaction. How fast is a reaction taking place? So there are various ways in which we can actually calculate the rate of reaction, okay, because we can use a change in concentration, a change in mass, a change in moles, a change in volume, okay, any one of those, if we divide it by delta T, it would be able to tell us the rate at which this reaction is taking place. And of course, the units would differ for each one. Okay, so the rate of the reaction can be determined by the rate of change of the reactants or the products. Okay, how fast we're using up the reactants would tell us how fast the reaction is taking place, or how fast we're forming products would tell us how fast the reaction is taking place as well. Okay, so yes, then we discussed the collision theory. Okay, particles must collide with enough energy greater than or equal to the activation energy, and particles must collide with the correct orientation. Okay, this is all part of the collision theory. In order for reactions to occur, in order for the bonds to form, the particles need to collide, okay, and then they need to collide in a specific way as well, and those things are mentioned according to the collision theory. Okay, then we discussed the 5 factors that influence the rate of reaction. Okay, we said that the first one is temperature, then concentration, pressure, catalyst, surface area. So if we change these things, they will have an effect on the rate of reaction. Okay, so temperature defined as the average kinetic energy of the particles. Concentration is the number of molecules per unit volume. Pressure is force per area. A catalyst speeds up the reaction by lowering the activation energy, right? A catalyst is a, okay, that's its definition. That's what it does. Surface area, the smaller the particles, the larger the surface area. That's just to define it. But the larger the surface area, the higher the rate of the reaction. Okay, so remember we compared the different surface areas in this little diagram. Again, I'm still yet to edit this document, but eventually I will edit it. And then we said colliding with correct orientation. Okay, then we said using the collision theory to explain why a certain reaction has a higher rate of reaction than another. Of course, comparing their temperatures or their concentrations or their pressures, or whether the fact that one has a catalyst or one used a different surface area, right? They will ask you to compare 2 different rates of reactions with 2 different reactions, okay, with different reaction conditions. One might have a different temperature, higher temperature. One might have a higher concentration. One might have a higher pressure. One might have been, one might have used a catalyst, okay, one might have had a different surface area, okay, the compound had a higher surface area, for example, okay, and then this is how we use it. So we mention the factor, so that's mentioning one of these 3, sorry, one of these 5, you define it, Okay, so mentioning it, for example, temperature, you can, if you're comparing the reaction of two different temperatures, two different reactions with different temperatures, whichever has the higher one will have a higher rate of reaction. Okay, for example, if reaction A has a higher temperature than reaction B, you will mention the factor. So you will say, since reaction A has a higher temperature than reaction B, reaction A's the average number of kinetic energy, of particles, average kinetic energy. So you can say the average kinetic energy of particles is higher in reaction A, which means more particles have sufficient kinetic energy, there are more effective collisions per unit time, therefore there is a higher rate of reaction. Okay, so that's how you can use it to answer the question. So when I say mention the factor, that's what I mean, to mention this part. Okay, cool. So let us move on. We discussed the exothermic and endothermic graphs, the potential energy versus course of reaction graphs, where in the exothermic, the main difference, okay, is that as you can see, it goes, the energy of the products goes past the energy of the reactants, whereas for the endo, the energy of the products do not pass the energy of the reactants. So you can see clearly that in the exothermic, the energy of the products is lower than that of the reactants. Whereas in the endothermic, the products have a higher energy than the reactants. Okay, or the other way to look at it is if you look at the energy released versus energy absorbed. In the exothermic, the energy absorbed compared to the energy released. So the energy released is higher than that of the energy absorbed. That's in the exothermic. That makes sense, right? Remember, in an exothermic reaction, more energy is released than absorbed. Okay, and please note that in an exo, there is still energy absorbed. It's just that there's more energy released than absorbed. And in an endo, there is still energy released. It's just that there's more energy absorbed than released. Okay, but those are characteristics of each one. So here we can see energy of reactants. Okay, we can see energy of reactants. We can see the energy absorbed, energy released, activation energy, the energy of the activated complex, the activated complex itself. Okay, where the products stand, where the reactants stand, where the products stand, and their energy respectively. We can also see a delta H. Okay, delta H is less than 0 in exothermic. Delta H is enthalpy, heat of reaction, and in endothermic, delta H is greater than 0. Okay, delta H is calculated by saying EP minus ER. Okay, then we discuss the effect of a catalyst, okay, on the rate of reaction. So we know that the catalyst lowers the activation energy, okay, but what we need to know is that the reaction products and reactants remain unchanged. So it doesn't affect the reactants in any way. It doesn't affect the products in any way, okay? It just gets us from reactants to product faster. Okay, it reduces the rate of reaction by speeding up, it speeds up the chemical reaction, okay, by lowering the activation energy. So you can see with a catalyst, so this is the regular one, okay, and then with a catalyst, okay, you can see that we start off with the same reactants, it just doesn't go all the way up to that old activated complex because the energy activation has been lowered, all right, so it doesn't need to reach that high energy level. So it just goes there, it's a quicker path and goes to the exact same products, forms the exact same product. Okay, so this is the effect of a catalyst. Then this is where we ended, the Maxwell-Boltzmann energy distribution curve, okay, where we discussed this is what the curve looks like, okay, for a reaction. And we have this line, which is our which represents our activation energy. Okay, so this is number of particles / molecules versus kinetic energy graph. So at some kinetic energy, which is located somewhere here, it represents the energy of activation. Okay, that part, this point of the kinetic energy represents how much energy is required in order for the reaction to occur. Okay, and then remember again, this is what the y-axis that contains a number of particles or molecules, okay, in general. So the higher we are, the more particles we're dealing with, right? The more to the right we are, the higher the kinetic energy we're dealing with. Okay, cool. So, yes, anything, okay, any value of number of particles on the graph that are past the activation energy, these would represent, okay, all of these, I'm just taking them to the y-axis, that represent number of particles, right? All of these values here. Okay, all of those values, they represent the number of effective collisions, okay? Because these are the collisions that have passed the activation energy. Since they have passed the activation energy, that means that they have an effective collision, okay? Because in order for an effective collision to occur, the particles need to have sufficient kinetic energy more than or equal to the activation energy. So everything that's past the activation energy would be an effective collision. So all of these are effective collisions. Okay, we just drew them as if they were particles that existed all over here. Okay, so all of these are effective collisions. Okay, now we're going to discuss the factors. How do they affect this graph? So making certain changes. Okay, and the first one we're going to discuss is concentration. Okay, now with concentration, it basically increases the graph. Let's do this. Okay, with concentration, it basically increases the graph. The graph becomes bigger, it goes higher actually. And curves down. Okay, let me explain it slightly neater. Okay, so when we increase the concentration, this is what happens to the Maxwell-Boltzmann energy distribution curve. Okay, as you can see, the graph has changed by going directly up. Okay, increasing upwards. Okay, and as a result of that, what you'll notice is now there are more particles that fall after the activation energy. There are more particles that fall after the activation energy. That's why we can say that an increase, this is why how this graph shows that an increase in concentration would increase in the number of effective collisions, hence increasing the rate of reaction. Okay, so as you can see, this is how concentration increases the rate of reaction because it actually increases the number of effective collisions. Okay, and this is how it's shown in this graph specifically. Okay, so for concentration, I'm just going to write notes here. For concentration, okay, how is the graph affected? This is just so that in the exam you're able to identify it. So you can just identify it by looking for this. The graph goes straight up. Okay, so the graph goes straight up to increase it in that way. Okay, and then you'll see, for example, with temperature, how is this affected? Temperature basically flattens out the graph, or yeah. So temperature, what happens with temperature? Okay, the graph gets flattened out like this. Okay, the graph gets flattened out. Okay, and because it gets flattened out in this way, you can see that it spreads further past the activation energy. So in fact, now instead of just having, so just remember the original rate of reaction, or the original amount of effective collisions, is represented here, right? These are the only effective collisions originally. When there was an increase in temperature, it now included all of this. Anything that's past the activation energy, it included all of this. Okay, so you can see that therefore there's clearly an increase in the number of effective collisions compared to the first one. That's with the increase in concentration. Now with the increase in temperature, it's all of this. Okay, so instead of just the blue, it's now this entire highlighted portion. Okay, I hope that makes sense. So this is the extra bit. And of course, it would be all of this as well, but I'm not going to go over it. It would be all of this that's extra when there's an increase in temperature compared to the original equation. Okay, but I'll just write it like that for now. Okay, and then we can say temp. I'm just going to put temperature. I'll rewrite everything neatly at some point. Okay, the temperature with temperature, the graph becomes more flattened, basically. And that's how we can try and identify if there's been a change to temperature in a Maxwell-Boltzmann graph. Okay, we can identify it in that way by looking for the part if the graph, because sometimes they'll call this reaction 1 and they'll call this reaction 2, and they'll say which reaction took place at a higher temperature. So you need to look for the curve that's more flat. Okay, and well, yeah, the one that's more flat, because that's how you identify what an increase in temperature, how would it affect this curve. Okay, and then there's one more thing, one more thing, and that is if we add a catalyst. So adding a catalyst, how does that affect our graph? Adding a catalyst, basically the activation energy moves to the left. Okay, the activation energy moves to the left. So instead of the activation energy being here, the activation energy may be found here now. Okay, and you may ask, okay, how does that increase the rate of reaction? Also increases the number of effective collisions, because now the activation energy is more to the left. So instead of this original blue part, is that being the only amount of effective collisions, it would now include all of this extra, right? I'm talking about just for the original graph. All of this would be included extra. Okay, all of that would be extra now with the what you call it, with the catalyst, right? With the new reaction having a catalyst. So therefore it has some more effective collisions, higher rate of reaction. So I hope you guys understand how changing concentration, well, an increase in concentration, an increase in temperature, and the addition of a catalyst increases the number of effective collisions and ultimately increases the rate of the reaction. And that's what's displayed on the Maxwell-Boltzmann energy distribution curve. Okay. Okay. So, okay, we can discuss this formula, percentage purity. This is just because I just want to put in these formulas in the notes because they do test these in rate of reactions, percentage purity and percentage yield. Okay, just remember that percentage purity is the pure mass or pure moles, right? It doesn't matter. As long as both pure and impure, you use the same unit. So pure over impure times 100. Percentage yield is the actual over the theoretical times 100. Always remember that the theoretical you get from your calculations, always. Okay, you always get them from the calculations, from the stoichiometry that you do. And the actual value they'll have to give you, okay, or unless they want you to calculate if they give you the percentage yield, like this percentage, but a lot of the times, actually, you cannot know the actual until you actually conduct the experiment or conduct the reaction. Okay, so the actual either have to be given or they'll require to calculate it, provided that percentage yield or percentage purity is given, the actual percentage. All right, so yes, theoretical, remember, is always obtained from your calculations. Whatever we work with in stoichiometry and rate of reactions, any calculations that we do using all the formulas that we know are purely theoretical. Okay, we're not carrying out the experiment as we do the calculations. They're purely theoretical. They don't take into consideration external factors such as the environment temperature, and so on, right? Whatever else can possibly affect the outcome of the reaction, we don't take that into consideration because we're just doing the calculations, assuming that ideal conditions are taking place. Okay, these graphs, I want to discuss them. They might look weird and you might never have seen them in rate of reactions. But either, okay, maybe let's just discuss them now on time. Okay, so these graphs basically represent, I want them to represent, how would they be labeled? Okay, they represent, okay, first they all versus time. Okay, and they could represent mass, volume, moles, okay, anything that we can measure change in. Okay, so I'm just going to put them all as mass or even concentration, I suppose. Let's just put concentration. Okay, so clearly these graphs are depicting the change in concentration versus the change in time. Okay, so for example, this one, okay, it could be, again, it could be mass, volume, moles, concentration, anything that we can measure a change in that would show a change in the reaction specifically. Okay, so let's just say that this guy is a change in mass versus time. So the change in mass versus time, as you can see, the mass itself is increasing with respect to time. The mass itself is increasing with respect to time because maybe initially you started off with 5 grams and now we ended up with 100 grams. Just random numbers, an example. Okay, it's increasing. Okay, mass versus time. As you can see, the mass is increasing versus time. Now let's talk about the gradient. Okay, so I don't know if you guys remember or if I even told you, but in physics chemistry, whenever you're working with gradient, okay, we can use y2 minus y1 over x2 minus x1. That is true. We will use it to calculate the actual gradient. But to determine what variable the gradient gives us, what does the gradient give us, we can always say the change in y-axis over the change in x-axis. The change in y over the change in x. So in this case, if our y is mass, the gradient gives us the change in mass divided by, what's our x-axis? Time, divided by the change in time. Okay, now, as you can see, the delta m divided by delta t is one of the options that gives us rate of reaction. Okay, so from this, we can see that the gradient actually gives us the rate of reaction. Okay, this is important. This is a skill that's important to have to be able to determine what does the gradient give you in physics and chemistry. Okay, so I'll go through it one more time. In this case, we want to determine, this is not mass, by the way, this is gradient. Okay, so let's just not put m, let's put gradient, just to not confuse the two. So this is the gradient. The gradient is delta y divided by delta x. Whatever's on the y-axis divided by whatever's on the x-axis. So here we had mass on the y-axis and time on the x-axis. So we said delta m divided by delta t. And we know that that gives us the rate of the reaction. So for all of these graphs, okay, the gradient gives us rate of reaction. Why? Because here the gradient is equal to delta C divided by delta T, which is equal to rate of reaction. Here the gradient, okay, same thing for the rest, right? Because I didn't choose something different. I suppose let's use volume here. So now we can say that the gradient is equal to the change in volume divided by the change in time, whatever's on the y-axis divided by whatever's on the x-axis, and that's rate of reaction. Here, let's use moles. So the gradient is equal to the change in moles divided by the change in time, which is equal to the rate of reaction. So the gradient for all of these graphs gives us the rate of reaction. Now I want to talk about these curves, these specific type of curves. Okay, are they increasing curves or are they decreasing curves? And why is that important to note? Because, well, it's important to note because we need to know whether the rate of reaction is increasing or decreasing. If we have an increasing rate, we would have to have an increasing gradient. Increasing gradient would result in an increasing rate. Let's do it in blue. Increasing gradient would result in an increasing rate. Okay, a decreasing gradient would result in a decreasing rate. Okay, and these are questions that they ask in the exam. Is the rate of reaction increasing between times this and that? So we need to note that here, even though, okay, so here we can see an increasing gradient, right? Let's put it that way. So the mass is increasing, that's correct. And the gradient is also increasing. However, on this graph here, even though the concentration is increasing, this is a decreasing graph. It is a decreasing slope graph, a decreasing gradient graph. So even though the concentration overall is increasing, right? The concentration is going up from 5, 6, 7 until 100, for example. Okay, that's very high. The slope itself is decreasing. So the rate at which the concentration is changing, or the rate at which the concentration is increasing, is actually decreasing. The rate at which it's increasing is decreasing. And the rate at which something is increasing or decreasing on this graph is known as the rate of the reaction. So here on this graph, the rate of the reaction is increasing, but on this graph, the rate of the reaction is decreasing. Okay, I hope I'm making sense. And one way to understand whether something is increasing or decreasing, look at the slope. So here my slope is more flattened, but as I move along further, I can see the slope is becoming steeper. That's the main thing. Is the slope becoming steeper or less steep? That's the big thing. Okay, so here you can clearly see that the slope is becoming steeper. So that means the rate of the reaction is increasing. That's what you need to remember. Here, the slope is becoming less steep. It's becoming more, what do you call it, shallow or flattened. Because here you can see a very steep gradient. But as we go here, it's becoming more and more flat. Okay. So let's look at this one, a decreasing graph. Okay. But is the gradient increasing? So it's going from quite steep to quite flat, actually. So in this case, it's a decreasing gradient. And here we have an increasing gradient. Okay, because it's becoming more and more steep. Okay. And here, this would most likely be, because here we have an increase in mass, this would most likely be a products graph. Yes, here too, increase in mass, most likely a products graph. Here we have a decrease in volume. Sorry, this was concentration. Here we have a decrease in volume. So this is most likely a reactant graph. Here we also have a decrease in moles, so that's most likely a reactance graph as well. Okay, please, if you don't understand this concept, ask questions and I will explain it again, but this is an important concept to understand. Okay, but yeah, that's us for the theory. Let us try and move on to do a question. Okay, question number 5. And we'll probably try and spend another lesson on a question. Let's just see how it goes, because actually for this section, rate of reactions, there's not much theory. Okay, I still did like some graphs extra and went through his graph and so on. And this year, but this is not really considered in the theory of rate of reactions. The main way to learn rate of reactions is to actually do questions, because the questions, I don't know, they're not exactly like what the notes teach, if I can put it that way. So that's why you have to do questions to understand the section properly and to be able to answer questions on your own. Okay, question number 5. The reaction of calcium carbonate, CaCO3, and excess dilute hydrochloric acid, HCl. Okay, don't worry about this excess for now. All right. When we deal with limiting reagents, we'll discuss this, right? Obviously, we'll deal with limiting reagents in like acids and bases. Acids and bases. Okay. So we'll discuss this concept, but for now it's fine, right? We'll come back to it and truly understand why are they saying excess dilute hydrochloric acid. Okay, that's important for us to understand, kind of, but kind of not also. So the reaction of calcium carbonate and excess dilute hydrochloric acid, HCl, is used to investigate one of the factors that affects rate of reaction or reaction rate. The balanced equation for the reaction is as follows: CaCO3 plus 2HCl excuse me, gives us CaCl2 plus H2O plus CO2. The same mass of CaCO3 is used in all experiments, and the temperature of hydrochloric acid in all experiments is 40 degrees Celsius. The reaction conditions for each experiment are summarized below. So, anything we need to discuss from above? No, let's continue. So let's compare the different experiments. So we can see the volume of HCl is the same in all, the concentration of HCl is the same in all. However, the state of division, which is basically the state in which the compound is, so solid, not solid, liquid or gas, the surface area. Okay, so we have granules, lumps, and powders. So firstly, powder has the highest surface area. Okay, then it is granules or lump. I can't really remember. Let me Google. I remember there's an image that I had. I will give it to you guys. Let's see which one has the highest surface area. I believe granules have the highest surface area. Okay, so the order of surface area, okay, the largest surface area is powder, okay, because that's the most refined, right? It's the smallest particles. Since it's the smallest particles, it reacts much more easily, right? Remember we discussed it in terms of that little container. Let's go back up to it actually. We can see that when something's a solid versus when something's a powder, for example, okay, when something's a solid, okay, what happens is the outside particles need to react first, and then eventually it will get to the inside. But when something's a powder, all of this solid is crushed into fine particles, and it's almost like every particle is exposed. Okay, so when we react to the powder, it's almost like every single particle of that powder reacts at once, and the reaction takes place much faster compared to reacting with the outside, then the next layer, then the next layer, then the next layer, and eventually getting to the middle. Okay, so that's the same thing when we think of powder, right? So powder has the highest surface area, therefore the highest rate of reaction. Then granules is number 2, and lumps is number 3. Okay, granules are like little balls. Okay, they kept in that form, and lumps are basically like heaps. Okay, heaps of a certain amount of compound. Okay, very thick. Okay, let's have a look at the questions. 5.1. For this investigation, write down the dependent variable. Okay, so dependent variable versus independent variable. Remember, the independent variable is the one that is changing, or the one that we are changing. Okay, the one that is being changed in the experiment. And dependent is the one that is being affected by that change. So as we can see from this table, the one that's being changed in the experiment is actually the state of division. So the independent is the state of division or surface area. That is the independent variable. That's the one that's changing. The thing that's being affected in this, when we change the state of division, is actually the rate of the reaction. And mostly for rate of reaction questions, the dependent variable is the rate of the reaction, because that's what we're comparing. That's what the section is. We are testing different conditions, different factors to see how it affects the rate of the reaction. So that's a dependent variable. Okay, let's have a look at this. We have carbon dioxide gas, CO2 produced during experiment A is collected in a gas syringe. The volume of gas collected is measured every 20 seconds and the results obtained are shown in the graph below. So just by looking at the graph, you should be able to tell that this is a product graph. Why? Because we see an increase in its volume in this case, an increase in its volume, therefore it's a product. It's not being used up, it's being formed. Secondly, you should be able to tell that overall, this is a decreasing slope graph. So the rate of the reaction is actually decreasing as we going with time. Okay, so volume of CO2 being produced from 0 to basically 60 seconds. Okay, anything we need to note? No. Okay, 5.2. Okay. What can be deduced from the graph regarding the rate of the reaction during the time interval 20 to 40 seconds? So from 20 to 40 seconds, what can be deduced from the graph about the rate of the reaction? So if you remember from those graphs, those graphs that we discussed, this type of gradient is a decreasing gradient, which means that the rate of the reaction is decreasing. Okay, so what can be deduced? It can be deduced about what can be deduced about the rate of the reaction. The rate of the reaction is decreasing. Okay, what about from 60 to 120? So they want to know what can be deduced from the graph about the rate of the reaction from time interval 60 to 120. Here we can see that there is no, because it's a flattened graph, there's no change in volume versus change in time. So therefore, there is no rate of the reaction. So the rate of the reaction is 0 at that point. And that's just because even though we stop measuring at 120, at 160 seconds, the carbon dioxide stopped forming. Okay, that's when the reaction completed, most likely. So the rate of the reaction is 0. All right, let's look at 5.3. 5.3 says calculate the average rate, and they tell you in centimeters cubed per second at which the carbon dioxide is produced in the experiment. Now, from this, we need to remember, or for this, rather, we need to remember the rate of reaction. Okay, rate of reaction is equal to the change in mass, moles, concentration, volume over change in time. So in this case, they want it in centimeters cubed per second. That means volume per second. Okay, which is delta T. Now we basically need to also remember that rate of reaction is actually gradient. Gradient is equal to the rate of reaction. Yes, me. So basically, we need to calculate gradient in order to calculate the rate of reaction. So y2 minus y1 over x2 minus x1, essentially. Okay, so here we have, again, centimeters cubed per second at which CO2 is produced. So that's where we go to the graph. Now we need to first identify, is the graph given in centimeters cubed? Because we don't want to enter the wrong units, right? So it is given in centimeters cubed, so that's fine. We don't need to convert. If it was given in decimeters cubed, we need to convert to centimeters cubed before we put it into our formula. Okay, so they want the overall rate of reaction, so we don't have to, let's look at the question again, calculate the average rate at which CO2 is produced in the experiment. So they don't want it between a specific time. When they say calculate the average rate, what you want to do is you want to go to the end and you want to go to the start. And that's how you want to calculate the average rate for the entire experiment. So you're going to calculate the gradient from between these 2 points. That's essentially what you're going to do. So from the 500 centimeters cube volume mark, from the 0 to the 500. And remember, you're doing y2 minus y1 over x2 minus x1. If we do that, okay, y2 minus y1 over x2 minus x1, we will get, so we start off obviously at the bigger point. Y2 is 500, right? We take the y value. Y1 is 60. Okay, remember the experiment stops at 60, not 120. It's just that they carry on recording the volume still 120 seconds had passed. Okay, and they got 500, 500, 500, 500 because it wasn't changing because the experiment was done. Then we go all the way here. Sorry, y2 minus y1. So it's not supposed to be 60. I chose the x value. Y1 is at 0. x2 is 60. The time at the second place is 60 and the time initially is 0. So this becomes 500 over 60, okay, which we'll calculate to the bottom. But yeah, I hope this makes sense as to how we calculate the rate of reaction using this graph. Okay, firstly, rate of reaction is gradient. They said average, so we use the last values and the first values to calculate the average for the entire experiment. Okay, but yeah, that's basically we're using gradient. So yeah, this again is going to become 500 minus 0 divided by 60 minus 0, which results in 500 over 600, which is basically 8,33. Okay, and what unit do you give for rate of reaction? So that's question specific. They did tell us the units, but how do we deduce it here? Remember that rate of reaction or gradient, for example, was change in x divided by change in y, which was actually change in concentration divided by change in time. Concentration had centimeters cubed, seconds had seconds, time had seconds. If we take seconds to the top, it becomes centimeters cubed to the second to the minus 1, times second to the minus 1, because we took seconds to the top. Okay, so yeah, that's how we get either way, centimeters cubed per second to the negative 1. And if we verify it with the one they gave us, we can see it's centimeters cubed per second to the negative 1. Okay, so that's how we give units in this section. Let's look at 5.4. How will the volume of carbon dioxide produced in experiment B compared to that produced in experiment A? Choose from greater than, smaller than, or equal to. Let's read this again. How will the volume of carbon dioxide produced in experiment B compared to that produced in experiment A? Choose from greater than, smaller than, or equal to. So they are asking, how is the yield affected? Because CO2 is a product. Remember, yield is the amount of product we anticipate to form. Okay, so how will the volume of CO2? They're asking how will the product be formed, basically. How will the amount of CO2, be affected by a change in surface area? So as you can see, so we don't affect CaCO3, the amount. We just change the state of division. The volume and concentration of HCl remains constant. So basically, this is constant. This is constant. Okay, these are both constant. And they're asking how does the amount of CO2 produced affected? So the only thing that's changing is the surface area of CaCO3. The surface area is changing. So the surface area does not affect the amount of yield. It basically just affects the rate of the reaction. So the amount, because we're using the same amount of reactants in both reactions, in experiment A and B, or whichever one they're asking us to compare, I think it's A and B, right? Compared in reaction A and compared to reaction B, we're using the same amount of reactants. So therefore, we're going to form the same amount of product. So it's kind of like a trick question, right? How will the volume of CO2 produced in experiment B compared to that in experiment A? It's actually going to be equal to. Why? Again, because we use the same amount of reactants. When we increase temperature, when we increase concentration, when we increase pressure, okay, these things increase the rate of the reaction, not the yield. Okay, so just keep that in mind. It increases the rate of the reaction, not the yield. So surface area increase only affects the rate at which the reaction occurs, not actually the amount of product that forms. Okay, so in this case, product that forms in experiment B is same as A and same as C because we use the same amount of reactants. All right, let's look at 5.5. Okay. 5.5, a graph is now drawn for experiment C on the same set of axes. How will the gradient of this graph compare to the gradient of the graph for experiment A? Choose from greater than, smaller than, or equal to, and use the collision theory to fully explain your answer. So it might sound a bit tricky initially, but they're telling you a graph is now drawn. How will the gradient of this graph compare to? Okay, so how will the gradient of the graph? That's the main thing I wanted to highlight. How will the gradient of this graph compare? Now we need to remember from what I mentioned earlier. Let's look at this graph. If you had to draw one for experiment B, this is not correct. I'm just drawing it. Maybe it looks something like that. Nevertheless, they don't want to know how it looks. They want to know about the gradient. So we need to understand for this graph, what does the gradient give us? And if we remember correctly, gradient of most of these graphs and rate of reaction actually give us the rate of reaction. The gradient gives us rate of reaction. So when they say, how does the gradient compare? They are actually asking, how does the rate of the reaction of experiment A compare to that of experiment C? Okay, I hope that makes sense. So how does the gradient of this graph compare to the gradient of the graph of experiment A? So we have to compare them, all right? A and C, not the party, these experiments, okay? Granules versus powders. How does A compare to C? Do they ask that in that way? Yes, they ask how does C compare to A? Okay, they ask how does C compare to A? Yeah, I'm gonna answer it in terms of experiment C. So C, they use powder, and in A, they use granules. So clearly, experiment C has the highest surface area compared to experiment A. Higher surface area results in a higher rate of reaction. Okay, but we have to use collision theory to explain it, and that's this guy. Using collision theory to explain why a certain rate of reaction is higher than another rate of reaction. Okay, so here's how we're going to do it, and I'm going to answer it with the memo. We're going to say okay, there we go. The surface area of the calcium carbonate powder used in experiment C is greater than the granules, or the surface area of the granules, doesn't matter. I think both make sense. Greater than that, or maybe then greater than that of the granules used in experiment A. That's the first part. We mentioned the factor. We described the relationship, or which one has a higher surface area compared to which one in the certain experiments. We said that this one has a higher surface area than that one. Then what do they mention in the memo? Okay, I'm just putting it in point form, but you don't really have to. More effective collisions per unit time. And then what do they mention? Okay, so this is 4 marks. Okay, and then they mention higher rate of reaction. Why is this pen not working? Okay, so this one you only have to mention 3 points. Okay, and I don't know if you remember correctly, but I mentioned that you don't always have to write all 3 points. So here we must out have sufficient kinetic energy. I would write it as well, just in case. Okay. But here you're actually getting your 4th mark for answering this question. Choose from greater than. So I would say greater than, right? In experiment C, it's the gradient would be greater than. Okay. So you can even maybe mention here. Therefore, greater gradient. Okay, so the higher gradient, higher rate of reaction. We know that. Okay, we discussed that. So in this case, the gradient of this graph, how does it compare to that of A? It would be greater than. So here you get 1 mark for saying greater than, then you get your 3 marks here. 1, 2, 3 more marks, and in total 4. Okay. So yes, that's how you answer this question, right? Using collision theory. Always mention the factor. More particles have sufficient kinetic energy, more effective collision per unit time, higher rate of reaction. Okay, let's end it there. 5.6 we'll do next time. Assume that the molar gas volume at 40 degrees is that. Calculate the mass of that using experiment A. So this is geometric calculation. Feel free to attempt it on your own if you'd like, but for now we're going to end it there, and we'll continue on that question next week, as well as do another question, or rather on Monday, actually, when we have our catch up. So yeah, or Monday, but yeah. Cool. Thank you guys so much for joining. I hope that you have a beneficial holiday where you get enough rest and you rejuvenate and refresh, ready to go back into term 3. But yeah, thank you guys again so much for joining. I will see you guys on Monday, inshallah. Jazakallah khair. Assalamu alaikum.